So yeah, so this is work I did with Adrien Fikes and well, 2 other people that are here. So you've heard already about this indefinite causality. This is very confusing to hear myself like this. Yeah, so normally in special relativity, there's a definite causal order between events. So you get one of 2 options, either that 2 events or parties are space-like separated, which at the level of correlations translates in saying that the correlations are non-signaling, or one can be in the future light cone of the other, and in which case signaling correlations are possible. But so we're interested in indefinite causality. There's, as you know, as you've heard, there's many ways to achieve such a thing. There's the process matrix formalism, Deutsch CTCs, etc. And depending on what you allow, you can get really crazy things. But one thing that's negative about these things, most indefinite causality processes, is that they don't really have clear physical meaning. Well, you could argue that CTCs do have a clear physical meaning, but at least they would be hard to perform in the lab. So what we looked at here was basically the one example of a non-causal process that we know how to make, which is the quantum switch or superposition of causal order. So in a sketchy way for the moment, it's superposition of Alice before Bob and Bob before Alice. And we asked the question of what can you do with this resource for information processing? Already stuff was known, so there are query complexity problems for which there is a reduction from n squared to n. And there was also some problem of communication complexity for which using the quantum switch yielded increased success probability, but that there was no asymptotic advantage. So we tried to find something for which there wasn't a asymptotic advantage over causally ordered quantum resources. So it's the outline of the talk. I will first introduce the general problem of communication complexity. Then I will talk more precisely about the switch. Again, I will not talk at all about the process matrix formalism, but of course you can formulate it in the process matrix formalism. And then I will introduce the specific game, which we call exchange evaluation, which allows you to get this exponential savings. So communication complexity. So the setup is pretty simple. You have 2 parties, and each party gets some classical input, and they want to communicate in such a way that you can calculate some distributed function of their inputs. So if you're studying quantum communication complexity, then you can allow unlimited entanglement here, and then what you're trying to do is to minimize the amount of qubits that are sent from Alice to Bob. So yeah, there are many definitions, many things you can study in communication complexity. This is really the simplest case, one-way communication from Alice to Bob. Yes, so this is like the most stupid example that was not trivial that I could think of, the equality function. So Alice and Bob each get 1 bit, and Bob wants to output 1 if their bits are equal and 0 if they're not equal. Well, this can be achieved with deterministic success if you send 1 bit. So for this particular problem, sending it, well, it's also 1 qubit, so there's no quantum advantage for this problem. Okay, so why would you study communication complexity if you're more foundationally minded? Well, first of all, and this was the reason why classical communication was first introduced is that it's a setting that's simple enough so that you can prove things, but also not too trivial. So in the quantum case, it means that there exist functions for which there is provable exponential savings, so that don't rely on computational theory conjectures to say that quantum is better than classical. And also, it's a nice set of problems for which you can study generalized probability theories. For instance, it's known that if you have PR boxes, they trivialize communication complexity in the sense that only by sending one PR box you can solve every problem. So people had been trying to formalize principles such as that quantum mechanics is special because it's the best at communication complexity without trivializing it. It turns out it's not that simple. Like there's almost quantum correlations, for instance. But okay, I will not really talking about GPTs either here. I will be talking about, well, okay, so this is a small result, maybe a trivial thing, but that we did not find in the literature. It's a condition on the function such that there's no quantum advantage in this one-way communication setting. So it's supposed that the function written as a sort of a truth table view. So here are all the inputs for Alice, all the inputs for Bob, and this is what they need to output if they get such inputs. If all the rows of the truth table differ, then basically quantum resources are not really good. They give you, well, Alice must send full information about X, and then this is basically can be achieved via dense coding. And so you save only a constant factor of 2 compared to classical resources. The proof is very simple, so I decided to give it here. So, well, suppose that such a condition is satisfied, then you can recall this very basic result of quantum information that by sending a d-dimensional quantum state, you can only establish at most d squared different orthogonal states at Bob. It's just application of the Schmidt decomposition, basically. And this translated from dimensions into qubits, this means that 1/1/2 log of the size of the inputs space of Alice will be sufficient for winning at the game perfectly, because then she will be able to send all the information about her input, and Bob just has to calculate f. But what if she sends only 1 qubit less? Then there will be some inputs, x1, x2, such that the corresponding states received by Bob are not perfectly distinguishable, just because this was the bare minimum for having all states perfectly distinguishable. But then, by the assumptions on the function, there will be a y such that the functions are different. So fx1, y will be different of fx2, y, which directly implies that, well, if Bob has this y, and then he receives something, that he will not be able to know if he's supposed to output this value or this value. So yeah, that's it. Yeah, we will come. Well, this will be used later, of course. So now the quantum switch. Well, Mateus talked about it, but with the CTC interpretation, take maybe the more down-to-earth interpretation. Oops. So that you have 2 degrees of freedom, one which is a qubit, its path degree of freedom, which when it is 0, you have the other degree of freedom, this internal degree of freedom that goes first through Alice, who's then free to apply whatever gate she wants on it, and then to Bob. And if the control is 1, then it's the opposite. First goes through Bob, Bob does his quantum gate, and then Alice receives the system and applies whatever map she wants on it. So this has been realized experimentally. So in in practice, you have the control qubit to be a path degree of freedom of a photon. So I mean, here's a laser, so it doesn't, for me, I don't know, but it comes out here and then goes through a beam splitter. So you have amplitudes 1 over square root of 2 to go here or here. And if it goes here, then this would be Alice, which is free to act on the polarization degree of freedom with wave plates. Then it is reflected and goes through Bob, and then re-interfered here at the beam splitter to the third party, which would be Charlie. And well, if in the other path goes first through Bob and then through Alice. So this is fine. I want to talk first about a specific sort of black box computational problem that is the basis for the communication complexity problem that we'll be talking about later. So suppose you're taking some unknown unitaries from some set, and you have the promise that in this set either the unitaries commute together or they anti-commute together. And your job is to say, well, whether they commute or they anti-commute. If you were using causal quantum circuits, then we know that you need to apply one of the gates at least twice. So here, Alice is applying the U-way twice, and then you can answer the question. But if you have the switch, then you can do this in one query. So it's quite simple. If the control qubit is prepared in the state 0 plus 1, then you have the one part that goes first through Bob, first through Alice, then through Bob, and this other part that goes Bob and then Alice. So this is up to here. Then you have the beam splitter, which is the Hadamard done by the third party cleave, and you get this state. So if you're guaranteed that either this is 0 or this is 0, then either this amplitude will be 0 or this one, which will tell you that if you measure the control qubit in the computational basis, then you'll be able to know with certainty which of these two is true. Okay. So now we'll use this fact to build a communication complexity game. And the comparison we're trying to make is causally ordered quantum one-way communication. So it's the same as before, but just added a C for convenience to make the comparison with the switch possible. So Alice and Bob are receiving the inputs, and they're communicating in a straight line, so definite causal order. It's just that Charlie at the end needs to output the result of the function. Versus quantum switch, which, well, Alice and Bob, they're receiving some inputs. They need to apply a unitary, or more generally a CPT map, to the state, and then at the end, Charlie will do some measurements and output the function. So now we want to find a function where there will be, where you will need exponentially less qubits if you're using a quantum switch in comparison to the one-way. Yeah. So this game is what we call the exchange evaluation game. The input set separated in two parts for convenience. So one of them is a binary string of length n, and the other thing is a function which taking from this set of functions. So basically all functions from the binary strings of length n to 0 or 1, such that on the string full of zeros, it's 0. And the task of Charlie is to output this, which is Alice's function evaluated on Bob's input, as sum mod 2 of Bob's function evaluated on Alice's input. Then you can see directly that this, well, you need to convince yourself of it, but it satisfied this condition that we had earlier about the truth table. All the rows of the truth table are different. So you directly conclude Alice needs to send full information about her x and f, but there's a lot of possible functions. And the size of the input set is like this, so it's doubly exponential. So in terms of number of qubits, you take the log. It tells you need to send this many qubits to succeed deterministically at the task. But if you have the quantum switch, you can do it with only n qubits of communication. And you do it with using a specific encoding of your inputs in terms of a unitary that you apply on the target state. And this encoding is as follows. You first apply this df, which is a diagonal matrix in the computational basis that is all ones or minus ones, and that's depending on the value of the function. So here, and then you apply this generalized Pauli operator, which x1, well, it's the first entry of the binary string. So if it's 0, then you apply identity. If it's 1, then you apply x on the first qubit, and so on. And you can easily see, well, maybe not that easily, but it's a one-line calculation that they commute, these unitaries commute if the exchange evaluation evaluates to 0, and they anti-commute if the exchange evaluation evaluates to 1. So, yeah, the guys, they do this, and at the end, Charlie does the same thing as in this setup. So Hadamard then measures control qubit, and if he gets 0, he knows, well, whether he gets 0 or 1 tells him the answer of the function. So that's it. This is how you get the advantage, but this was only in the deterministic case, and it's known that when you compare quantum communication complexity, the normal one versus classical, sometimes just by adding a non-zero error, it destroys your advantage. So it was important to check what if instead of deterministic success, you ask that you have some epsilon such that for all inputs the probability of error is less than that. And well, you can show it still holds. It's, well, I don't want to explain what VC dimension is, but there is some bounds that are known, and you just apply them, and it works. So just so that you know it can be done. Yeah. So okay, well, there's some controversy about realizations of the switch. So you might want to argue, what is this advantage? Why is it not just two-way communication? Which, by the way, the exchange evaluation game can be done with something like 2n qubits if you allow two-way communication. So we need, and indeed, when you look at the switch in the lab, it looks more like this. You have one path goes through A at some time, and then B at some other time, or, well, B here, and then A. But these are 4 space-time regions. So, yeah, how is this different from two-way communication? Some people might want to argue you don't get the switch for real unless you do something like putting superpositions of space-time or something more weird. But you can come up with a way to count channel uses that is more or less realistic and that makes the difference between the switch and two-way communication. So the initial case we had was you have some Hilbert space and then you're applying a unitary on it back to some Hilbert space. But you can extend this to U tilde, which has the system Hilbert space and a counter Hilbert space. So the system Hilbert space is the same one as before, but you add some vacuum state, which corresponds in here to, well, like when you're in the green path, this guy would be getting the vacuum. It's just nothing happening. And then the counter, well, I put it 3, but could be, well, any dimension. And then you just define this U tilde and function, well, as a function of the original UA. So if you receive a system vacuum, then you just do nothing. And if you receive a proper state, so something that belongs to this H, then you apply the unitary and you increase the counter by 1. And then you can, well, you easily see that for the switch at the end of the story, both parties will have their counters in 1, while if you're doing real two-way communication, then one of them will have 2. So it's sort of a, in principle, way to argue that you can establish this advantage for real and really say, I was not doing two-way communication, I was using the switch. So that's it. I think maybe I'm under time, but I have nothing more to say. So I hope this convincing that the superposition of causal order can be an interesting resource for information processing. I talked about the exchange evaluation game, which is the task for which we found an exponential advantage. And, well, this technical point that it makes sense also in the real world where you have bounded error. So that's it. Thank you.